Hello and welcome everyone to the interactive live session tutorial for week 4 content. Hope I am audible to you. Can anybody please confirm that?
Yes, you are.
Okay, thank you. So this week content the syllabus covered is about the impedance matching in microwave networks. So, the lectures had discussions on impedance matching using L section and series stub network. And second lecture was on impedance matching using shunt stub, double stub, quarter wave transformer. And the third lecture was on multi-section matching networks and tapered lines. So these were the contents covered in the previous week or the week 4. So as you all have already watched the video lectures, you have some idea of all these. So I hope the fundamental concept of this impedance matching is clear to you. Say you have a transmission line having a characteristic impedance Z0 and you have a load which is denoted like ZL, load impedance, and because this Z0 is not same as ZL, I hope you know what will happen because Z0 is not equal to ZL. There will be reflections. You don't have maximum power transfer. So therefore we require something called as matching network, which is the fundamental concept for this whole week 4 content. So different types of matching networks are possible. Among them, these L section is the one which is started out with. Then we have the series step. Then we have the shunt step, double step, quarter wave transformer, and you also have some multi-section matching networks. That means multiple sections of transmission line on the lines. So to start out with giving an introduction to L section, as the name suggests, it's in the shape of letter L. So if you have a network like this, JX and JB, so these are the reactive elements, and then you have ZL, which is the load, and Z0 is the characteristic impedance of the transmission line. So this kind of a L section matching network will work under one condition. So I hope you know that condition. So real part of ZL, that means real part of ZL means real part of the load impedance, or we call it as RL, should be greater than Z0 for this kind of a L section. Say if it's the other way around, for RL less than Z0, we have JB, JX, ZL, and this is Z0. So this is the kind of L section network used when RL is less than Z0. So this have been discussed in detail in the video lectures. The derivations, everything have been discussed. So our aim of this session is to work out some numericals based on this. So I will not go into the details of any of the derivations or how it is being achieved. So we will concentrate on how we look at the numericals to solve. And say example of a networks L section, I can just give you. This is an L section network where you have a series inductance and a parallel capacitance, or you can also have something like this: series capacitance first and then parallel inductance later. So these are the kind of actual L section networks which we use to for the matching of from Z0 to ZL. So let us concentrate on going into the detail, going into more of numericals. Okay, here the first question comes. L section matching network shown below is used to match the load when real part of ZL is greater than Z0. Is this true or false? Hopefully you can answer it now since we discussed it already. You can type in the chat what do you think, whether it is a true or false statement. Yes, it is a true statement. So this is the network when real part of ZL greater than 0. So this is a true statement. So let us move on to the next question. So this is about a quarter wave transformer. So before going into the question, let us give a short brief summary of quarter wave transformer. So similar to what we had as matching network, here it is quarter wave transformer, which is a transmission line having a length of lambda by 4. That is why we call it as quarter wave. Quarter wave is lambda 1 by 4th. So quarter wave transformer is a transmission line section having a length of lambda by 4. Okay. And now this is the characteristic impedance and this is the load impedance, and we need to have a quarter wave transformer. We don't know the impedance of this. Let us call it as ZQT. We don't know what it is. So how do we calculate what is the impedance of this? That means what is the characteristic impedance of this transmission line needed to match Z0 to ZL. So how do we evaluate that? ZQWT. That means the impedance of quarter wave transformer is square root of Z0 into ZL. This has been discussed in detail in the video lectures. So let us look at only the final formula. So the problem is a lossless quarter wave transformer is used to match a 50 ohm load. That means ZL is 50 to a 100 ohm line. That means Z0 is 100 ohm. Now characteristic impedance of the quarter wave section is, so we have been asked to find ZQWT, that is nothing but square root of Z0 into ZL, which is root of 100 into 50, which comes out to be 70.71 ohms. So option C. This was a very simple problem, very simple type of matching network. So quarter wave transformer. So if you could notice, there is some limitation with this kind of quarter wave transformer. So the length is dependent on wavelength. So once if the wavelength change, the length has to be changed. So this is the kind of limitation for a quarter wave transformer being used as a matching network. Okay, let's move on to other problem. I hope this is clear. There might not be any doubts because it's a very simple numerical. Although if you have any clarifications, you can just let me know. Okay. Okay, so going to the third problem. See, as you can see in this figure, you are given with a LC network, which is a matching network. So here, as you see in this problem, this is our matching network and this is ZL and this is Z0. Okay. Now, let us look at the question. L section matching network shown below is used to match 100 ohm load. ZL is equal to 100 ohm and Z0 is equal to 50 ohm at 500 megahertz. So the frequency is also given 500 megahertz. If the value of L, So value of L is given to you, that is L is 50 pi. Then find out C. So how do we find this? So we have some relationships derived during the video lectures. So if you could remember, C is equal to B by 2 pi F, and where B is equal to XL plus or minus root of RL by Z naught into square root of RL square plus XL square minus RL into Z naught, all divided by RL square plus XL square. Here, can you tell me what is XL? It is a
Imaginary part of ZL.
yeah. So is it okay? Can you tell me what is the value of that imaginary part of ZL?
0.
0. So because it goes to 0, the expression for B reduces. So B becomes plus or minus root of 100 by 50 into root of 100 square plus 0 minus 100 into 50 divided by 100 square. So this you can calculate it to be plus or minus 1 by 100. 1 by 100. So once you know the value of B, it's a simple substitution in this formula. So C is equal to B by 2 pi F. 1 by 100 divided by 2 pi into F is 500 megahertz. So 500 into 10 power 6. So this comes out to be, so this plus or minus 10 by pi picofarad. So if you could notice, the information on L was not needed. So in fact, L and C can be calculated from the formulas itself. So that is something which you need to notice. So XL is x by 2 pi f and C is B by 2 pi f for such a network. So if at all these are being asked, you can calculate by knowing the value of B and X. So the formula for B and X you can get from the weekly notes for this course. So that is a direct formula and you can substitute the values and find out L and C. Okay. So this answer option is A. I hope there are no clarifications needed. So let us go to the next question. Okay, let me come to this question a bit later. Okay, we can try to solve this. This is something which you can try now because we have already discussed the concept. But if you notice, there is a small change here. Here C and then L. So it's a network like LC network, but not same as this. So here, given the operating frequency, that is f is equal to 500 megahertz, you need to find L and C for the impedance matching network given below. So I can give you the formulas for L and C. ZL by 2 pi f and C is 1 by 2 pi f Z naught. So it will be nice if you can try this out now and type in the answers in the text. You know the value of ZL and Z0, and you also know the frequency. So this network is something like this, which we have discussed before, JB and JX. So if you could notice, this is ZL and this is Z0. In the very beginning I had mentioned, whenever real part of ZL, that means RL, less than Z0, we use this kind of L section network. So you can notice that this is 25 ohms and this is 50 ohms. Can you please find out and get the answer, because it's almost the same idea, and the formula has been changed because the network is slightly different.
Ma'am, option A is right. 25 by 5 pi nanohenry and 20 by pi picofarad.
Option A. Okay. Okay. So I hope I can just give you some hints. 2 pi into 500 into 10 power 6, and this is 1 by 2 pi 500 10 power 6 into Z0 is 50. So once you solve this, you will be able to get the value of L and C. Okay. I hope I can go to the next question. Okay. So this question is not L section network. This is slightly different. So in the beginning I had told about series stub and shunt stub. That is also a matching network which can be used to match the Z0 to ZL. So consider a load impedance which has real component and reactive component, and this has to be matched to 50 ohm line with a single short circuited shunt stub. So now you need to understand what is a single short circuited shunt stub. Say you have a transmission line, and at the end of the transmission line you are connecting the ZL, which has 50 minus J75, and this is Z0 is equal to 50 ohm. Single short circuited shunt stub. Shunt means in parallel. So you have a short circuited stub. So this is the meaning of short circuited stub. So that's a small section of transmission line, okay, which is connected in parallel with the existing transmission line, which is short circuited. Okay. Now and there is only one such section. Okay, there is only one short circuited shunt stub. Now the question is the location and length of the stub. So we need to understand where this has to be connected. That means the location of the stub and also the length of the stub. So location of the stub is indicated as LS and length of the stub is indicated as LT. So I hope you remember the concept of normalized load impedance. So whenever you have a load impedance, to normalize that, what do we do? ZL by Z0. So here it is 50 minus J75 divided by 50. So this is the normalized impedance. So this turns out to be 1 minus 1.5 j. Now what is the length of the step? What is the location of the step? So if you have gone through the video lectures, you have the formula for LT and LS. So LT is stub length and this LS is location of stub. Okay. So this is lambda by 2 pi tan inverse of root ZL Z0 by ZL minus Z0. And the other location of stub is lambda by 2 pi tan inverse of root of ZL by Z0. So here, so you know ZL, Z0 and also you know the, so you are not given with the wavelength information. So you can get the stub length and location of stub in terms of lambda. So if you notice, the answer options are in terms of lambda. So you can find the answers in terms of lambda only. So this can be solved.
Ma'am, ZL we have to take the real part.
No, here you have the reactive impedance. ZL is combination of real and reactive impedance. So it is a complex number. ZL is a complex number.
Oh, that means inside tan inverse we have a complex number ZL.
Ah, yes.
Okay.
So let us go to the next question. That is for a two-section binomial transformer. So this comes out to be part of multi-section matching networks. So as you see here, there is a two-section binomial transformer. That is again a matching network used to match 150 ohm load to a 50 ohm line. Characteristic impedance of the two sections are. So you need to find the characteristic impedance of those two sections. So you can note down ZL is equal to 150 ohm, Z0 is equal to 50 ohm, and the general formula derived was ln of Zn plus 1 divided by Zn is equal to 2 raised to minus n Cn raised to minus n ln of ZL by Z0. So if n is equal to 0, that is the first condition. That means for a two-section binomial transformer, we have two of them. So ln of ZL by Z0 is equal to 2 raised to minus 2 C0 raised to minus 2 ln of 150 by 50. So the C0 coefficients can be found. Substituting that here, you can get an answer for ZL. That is for one particular section of the binomial transformer. For the second section, substitute n is equal to 2. Sorry, n is equal to small n is equal to small n is equal to 1 and capital N is equal to 2. Okay, please don't confuse with those things. So small when n is equal to, so the second transformer section, how do we take it? Ln of Z2 by Z1 is equal to 2 power minus 2 Z1 square ln of 150 by 50. So you have seen that C coefficients can be found, and you can substitute the appropriate values of C coefficients and get the answer for Z2. So this is actually a second section's characteristic impedance. So this is the characteristic impedance of the first section. This is for the second section. So please I think this looks little confusing. So this is Z1 and this is Z2. N is equal to 2 because we have two numbers of sections for the binomial transformer.
And ma'am, what is the equivalent after finding Z1 and Z2?
I couldn't get your question. Can you repeat, please?
Ma'am, the question is asked that the characteristic impedance of the two sections. So individually we have to find the two sections, or a single characteristic impedance of combination of the two sections?
No, it is individually the characteristic
Okay.
impedance of
Okay,
two
right.
different sections.
Yes, exactly. The answer is given in two answers are
Two
given.
answers you
Exactly.
have.
Exactly.
Now let us go to other question. So somebody has asked about C0 and C1. So if you have noticed the lecture videos, you have a table where you have the C0 and C1 coefficients, and then you can find the respective numbers. Right now I don't have that numbers with me. So it is direct from that table. Okay. So now let us go to tapered sections. So tapered sections being used as matching networks. So one of the example is exponential taper section is designed for matching a 100 ohm load to a 50 ohm line. So you have ZL is equal to 100 ohm, Z0 is equal to 50 ohm. So length of the taper section is, so I am telling the length of the taper section, L is equal to lambda by 2. Magnitude of reflection coefficient. Again, this is a direct formula to be used to find the answer. But let me try to tell you. So gamma, the magnitude of reflection coefficient is half ln of ZL by Z0 e raised to minus j beta L. So here into sine beta L divided by beta L. So this is the reflection coefficient. So if you notice, what is beta L? 2 pi by lambda into the length of this taper section is lambda by 2. So this comes out to be pi. So sine beta L or sine pi goes to 0. Okay. So the reflection coefficient is 0. So you can notice that. So we use a taper section to match this impedance to the other impedance. That means match 50 ohm line to 100 ohm load, and this exponential taper section has 0 reflection coefficient. So that is not introducing any kind of reflections. So that is very evident and clear, but still I wanted to make a note of that. So magnitude of reflection coefficient is 0. So we had another problem which we left. Let us go and do that. Okay. So here a load impedance of 50 plus J10 is to be matched to a transmission line of characteristic impedance Z0 is equal to 40 ohm using a length of a lossless transmission line of characteristic impedance Z1, value of Z1 is. So you have something like this. This is the transmission line's characteristic impedance, and then there is another section which has an impedance Z1, and there is a load ZL. So ZL is 50 plus J10. Now, if you look at this system, looking into this input terminal, what is Zing? That is input impedance. So you have already learned about Zing. Zin is actually Z1 into ZL plus JZ1 tan beta L. So if you notice, this is actually the formula from transmission line theory concept. So please note that this is Z1, but there we have denoted it like Z0. So please don't confuse. So this is the characteristic impedance looking into this terminal. So, and this is the load. So Z1 into ZL plus JZ1 tan beta L divided by Z1 plus JZL tan beta L. Okay. Now this is given to us. It is mentioned that you have this input impedance to be 40 ohms. Okay. Now let us, so what is being asked to us? We need to find what is Z1. So to find what is Z1, a little bit of difficulty is there because of this term tan beta L. So let us make tan beta L like a simple constant T. So because for a constant length transmission line, value of tan beta L will be a constant. Okay. So if you put tan beta L is equal to T and then try to equate the real and imaginary parts. So let us try to solve this. Z1 into ZL is 50 plus J10 plus JZ1 T divided by Z1 plus JZL, that is 50 plus J10 into tan beta L is taken as T is equal to 40. Okay. Now if you simplify this, what you will get? Z1 into 50 plus J terms, I can just join it, 10 plus Z1T, which is equal to 40 Z1 plus 40 J 50 T. J into J becomes minus 1 minus 10 T. Okay. And this 40 will be common here. Okay. Now equate the real parts. Try to equate the real parts. What do we get? So this is a real part. 40T Fifty into Z1 is equal to 40 into Z1 minus 400 into T. Okay. So this comes out to be 10 Z1 is equal to minus 400t. So 10 this cancels. So Z1 is equal to minus 40t. So this is by equating what? Equating the real part. So you get an equation once you equate the real part, that is Z1 is equal to minus 40t. Next, if you equate the imaginary part, same way you can try to solve this. So what happens? 10j, so I can just write it like this, 10 plus Z1t into Z1 is equal to, what is the imaginary part here? That will be 40 into 50. 40 into 50 for 2000 t. Okay. Okay, fine. Now 10 Z1 plus Z1 square t is equal to 2000 t. Okay. Now we have two equations. You can definitely find the value of t. So t, when you solve this, you get two answers. One is 0 and plus or minus root 3 by 2. Now please note this. Once if you make t is equal to 0, what will happen? Once t is 0, z1 will become 0. So that's not an option which can be possible. Now suppose if I make plus root 3 by 2, z1 comes out to be a negative number. That is also not possible. So we need to choose t is equal to minus root 3 by 2, which will give me the answer for z1. That is minus 40 into minus root 3 by 2. So this will be approximately 49 ohms. So this is the value of z1, that is the characteristic impedance of this particular section, which is used to match these two. Okay. So the answer option is B. Is there any doubts, any clarifications? If you have any questions, you can ask me. The number of problems which I have got is being done with. But still, if you have any particular doubts, you can ask me.
Uh, I was just wondering in the tapered line question, in the tapered section question,
Okay.
is there a way to just guess the answer that the reflection coefficient would be 0 just by looking at the numbers? Because it's a half wavelength stuff, and then the two impedances are just double of each other. I mean,
Yeah, you if you know the length of the transmission line, and you know that it is function of, so the gamma function is basically function of sine beta L. So you know that whenever beta L becomes the condition when beta L, so directly looking at the length of the transmission line, you may be able to guess this.
yeah. I mean, at least in the Smith chart,
Okay.
after every half wavelength,
Yes, yes,
the impedance repeats, right? So,
yes, yes.
yeah, we're just trying to draw a connection between that two. I mean,
Okay.
which are on this. But anyway, I think I'll have to think a bit harder on it.
Okay, okay. Yes, you are right. After every lambda by 2, the impedance is repeating.
Yeah.
Yeah.
Ma'am, could you please go to problem number 7?
Okay.
Ma'am, my doubt is this above one, ln z2 by z1 is equal to 2 to the power minus 2, c1 square or c1 whole to the power minus 2. Here one minus 2 has been put in ln
Oh,
z1 by z.
okay, okay, okay. Let me correct that. Yes, yes. Okay.
Okay, thank you, ma'am.
Yeah. It will be okay. Prashant Panda is asking C values. That means the coefficient. I hope you are asking about the coefficients, the C coefficients. Yes, it will be given to you in the exam. You need not remember that. And if you notice, there is something to be highlighted here. So, based on the impedance of the first section, I mean, so this is Z1 is being calculated and the impedance of the first section. So, that is being substituted here. So, if you notice, once you find the first section's impedance, that is the impedance coming here. That means it's like a transforming part. So the first section transforms to some impedance, then the next section is transforming to Z2. So it is a two section matching network or a binomial transformer which will match from 50 ohm to 150 ohm load.
I had a general question. Uh,
Okay.
I have never been into a microwave engineering laboratory,
Hmm.
but I was just wondering when you work with real stuff, when you have to design a impedance matching circuit, let's say, do
Hmm.
you really, I mean, solve all these equation and come up with the numbers, or there is some other fancy or I mean shorter way to just calculate?
Okay. So, to be very specific, like if you see, all these have been made into like uh, standard formulas, right? So, if you just put in the values of load and characteristic impedance, there are applications which will give you series stub impedance or series stubs length, position, and all that. Sorry, shunt stubs position. So see, now we have all based on all these fundamental equations, now we have the kind of applications which will directly give you all these numbers. So so rather in lab, I mean in an undergraduate level, definitely yes, we follow the equations and find out the value of L and C. So say in that case, yes, but when it comes to a practical scenario nowadays, there are a lot of applications which will directly give you the value of L and C. Not just this, many kind of networks, if you give off the numbers, they will give you the L and C, or they'll give you the length of the stub, so because all these are standard things, there is no question on the standard stuff. And there are also people who look at the Smith chart for coming to this final answers. Yeah.
All right,
Yeah.
thank you.
So if there are no doubts, we will try to close the session. Uh, Please, if you have any doubts, you can ask, or we'll try to close the session. I hope the sessions are helping you to solve the weekly assignments and keep up the spirit of this course. So I'm hereby closing the session. I hope there are no questions. Thanks everyone. Thanks for joining. Meet you next week, same time. Thank you. Thank you everyone.